The Opera House in Sydney, Australia, a jewel of modern architecture, but poor design sent costs soaring $130 million over budget. The Hancock Tower, Boston, another fiasco. For years, its plate glass windows fell out. 800 years ago, medieval master builders constructed towering monuments without the benefit of modern science. Now, engineer Robert Mark is casting new light on how these extraordinary ancient structures work. What lessons do the buildings of the past hold for those practicing architecture today?
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
This is urethane rubber. And of course, I can simulate bending on the model. And the bending pattern has this typical form of almost parallel lines, so that it's easy to distinguish one type of loading from the other.
Robert Mark is an unusual man. An engineer by training, he now teaches both architecture and civil engineering at Princeton University, and spends much of his time explaining engineering concepts to historians.
This is a model of the structure of the nave of Palma, Mallorca, and we've loaded this under dead loadings, and it illustrates very nicely the typical patterns that we saw in the urethane rubber model. The model illustrates...
The combining of structural analysis with historical studies often yields unexpected insights.
It works extremely well. I think what I would have had them do is to remove the flyer, perhaps raise the lower flyer a bit, and then perhaps...
His research provides a rare opportunity to understand the achievements of the master builders of the past and to reevaluate the work of architects today. Mark's exploration begins with the French architect Le Corbusier, one of the founding fathers of modern architecture. In the 1920s, he drew an unlikely comparison between the great monuments of ancient Greece and early sports cars. Like sports cars, Greek temples were the products of an intense evolutionary process, said Le Corbusier. Their near perfection was achieved only after endless refining and experiment. But this comparison is misleading. It was the engineering of sports cars that continually improved, while Greek temples simply changed in style. This is Paestum on the Bay of Naples. These temples were built in the 5th and 6th centuries BC. For architects like Le Corbusier, Greek temples became an ultimate standard for architecture, buildings to be emulated and revered. But whatever the perfection of their proportion, from an engineer's perspective, they leave something to be desired.
Greek temples have been much admired, and justly so for their wonderful style. But in fact, their structure is rather primitive. It was based on earlier post and lintel construction in timber. As you can see, the vertical column supports a horizontal lintel. The structure worked very well in timber, but it led to a great problem in stone.
simple structural analysis shows the shortcomings in the temple's design. Support a beam at its ends, and it experiences both compressive and tensile forces. As it sags under its own weight, the upper portion of the beam tends to compress. Stone resists compression. It is hard to crush. The beam's lower portion is stretched. It feels tensile forces. Stone is very weak in tension, and the spans of the temples had to be kept short. Even so, in places, the lintel beams have cracked and pulled apart.
The limitation in the span of the lintel meant that the structural development of the Greek temple came to a technological dead end. In fact, the development was largely one of style. That's very much unlike the development of the early automobile. There, the evolution was largely one of engineering. Le Corbusier failed to distinguish between the engineering and stylistic development.
In emphasizing appearance over structure, Le Corbusier served modern architecture poorly. Because, as Robert Mark's work is revealing, the real challenge for master builders is to do justice to both aesthetics and engineering. "700 years after the temples of Paestum were completed, the Roman Emperor Hadrian built a great domed temple, the Pantheon. One of the wonders of the ancient world, its scale still staggers us today.
For almost 1,400 years, this was by far the largest span building. In fact, even until the middle of the 19th century, there were only two other buildings that equaled its span. During the Middle Ages, they were so concerned about what was holding up the roof of this building that it was suggested, since it had once been a pagan temple, then perhaps demons were holding up the roof.
Creating this monumental space is much more challenging than building a Greek temple. How could the Romans erect such a colossal structure? Historians argue that the key lay in a new building technology, a novel form of concrete containing pozzolana cement, first developed in the town of Pozzuoli near Naples. But Mark discovered that the Pantheon's secret is more subtle. His interest focused on the exterior shape of the dome and on a curious series of rings found there.
The original dome was even more exciting than it looks today because it was covered with bronze. But the bronze was removed later on because of its great value, and now the dome is covered with lead. The most interesting structural feature from my point of view are these step rings that encircle the entire dome, and they've been used on later buildings as well. The major question is just what structural function they have.
Step rings became a characteristic feature of Roman domes. But when Mark first analyzed the rings, their presence made little sense.
This is a model of the Pantheon that we've constructed in the computer, and the cross-section of the model is shown in yellow. The computer knows that this is really a three-dimensional structure, and what you see is the dome, and then the step rings in the lower portion of the dome, and then the wall, which is 6 meters thick in the actual structure. The model then is programmed to find the deflections and the stresses caused by the dead weight of the self-weight of the structure itself. And I can call for that deflection. The blue pattern developing shows how the model deforms. The deformation that it shows is greatly exaggerated, but it explains the mechanism of deformation. The dome, as you can see, drops down quite a bit from the yellow to the blue, and as it does that, it pushes the walls outward. And that outward pushing of the walls, in fact, builds tensile stresses along the circumference. If you think of a rubber band along the exterior of the wall, as it moves outward, it stretches the rubber band. And that's exactly what's happening to the concrete in the actual structure. The image on the screen shows those stresses that are caused by the expansion of the Pantheon walls as the dome falls downward. The red region shows the points of appreciable stress. It's been assumed that the step rings would reduce those stresses. So we looked at the model without the step rings to see what would happen. And in fact, we found that the stresses were reduced without the step rings. The step rings did not provide reinforcement to the building. So this created a question: just why were the step rings applied to the structure?
There is a crucial difference between Mark's first model and the actual building. The model assumes the dome acts as a single piece of concrete, a monolith. In fact, the dome is cracked into a set of pie-shaped wedges. When the computer model was allowed to crack, the results of the stress analysis were quite different. This time, with the rings absent, considerable tension develops, as the red areas indicate. With a cracked dome, it seems, the rings make all the difference.
We've added the rings now in the cross-section, and the effect of the rings is to reduce the tension considerably. As you can see, there's a great deal less red. In fact, what's left is really negligible. The Romans apparently understood very well that by putting additional weight over the support to the dome, that they could reduce the kind of tension stress that we saw in the section without the rings.
Whether or not the builders expected the dome to crack, the design of the Pantheon was not entirely a leap in the dark. The cracked dome acts like an arch. If there was one structural device the Romans understood, it was the semicircular arch. They used them everywhere. This is the Villa Adriana near Rome, and like the Pantheon, it was built by Hadrian. In an area known as the Maritime Theater, Mark found the evidence he was searching for, a segment of barrel vaulting, which structurally is simply a series of arches placed behind one another. Its profile is strikingly similar to the Pantheon's dome.
An arch thrusts outwards because of its weight, and the early builders learned to put additional weight down over those supports to stabilize the arch. The resemblance between the shape of the surcharge over the vault and the step rings in the Pantheon led me to realize that the builder of the Pantheon was doing exactly the same thing. His step rings weren't acting as rings at all, but they were acting as surcharge. And I have no doubt that it was his experience in building probably many arches and vaults that led him to use the step rings in the Pantheon.
The Romans ensured success by building on their past experience. The step rings are both decorative and perform a vital structural function. Later master builders were not always so fortunate. St. Peter's Basilica, also in Rome. When it was completed in 1590, it was the largest church in Christendom. Most of the great artists of the Renaissance, including Michelangelo, contributed to its design. Not since the building of the Pantheon more than 1,300 years earlier had such vast spans been attempted. When they decided to erect the dome so far above the ground, its builders created new problems.
Renaissance domes were intended to provide large sculptural forms against the skyline. To accomplish that, they raised the domes up on tall cylinders, and they often had large central lanterns. The lantern here at St. Peter's weighs hundreds of tons. All of this caused critical structural problems in the domes.
The dome of St. Peter's lacks the solid surrounding walls of the Pantheon, but the structure of the dome, a double shell of brick and stone, has little to stop the outward spread as the weight of the dome and the lantern pressed down. Cracking became evident almost immediately, and a series of massive chains now encircle the dome. There are better ways to build large domes. One was used in London in the Dome of St. Paul's. When its architect, Sir Christopher Wren, planned his grand design, he was probably aware of the problems at St. Peter's, as Robert Mark's colleague, historian Alan Borg, explains.
Sir Christopher Wren was Britain's greatest architect, and this is his greatest building. But he didn't start off as an architect. He was a scientist and professor of astronomy at Oxford University. It almost took a disaster to turn him into a successful architect. The Great Fire of London in 1666 destroyed the city and the church that was here before this, and Wren rebuilt it. But he had in fact been asked to do some repairs to the old Gothic church that stood here beforehand, and what he planned to do was to put on it a central dome, the first dome to have been built on an English church. When that church burnt down, he kept the idea of the dome and retained it for this, his great masterpiece. One of the best ways of discovering the secrets of the dome of St. Paul's is to look at these splendid drawings by Arthur Pooley. Here we see one which shows the side of the cathedral very much as the visitor would see it, with the splendid outline silhouette of the dome. But the next plate shows a cutaway section of that same view, and this reveals the complex structure underneath. The dome we see from the outside is really no more than a timber shell covered in lead. Then the visitor on the inside sees another dome entirely when he looks up, a light brick dome with the paintings of Sir James Thornhill on it. And then between the two, as this drawing clearly shows, is a cone of brick.
In Wren's ingenious solution, it is the cone which carries the primary loads of the dome.
We're actually standing inside the brick cone, which is the part of the structure that is doing the work, that is holding up the lantern. It doesn't look particularly like brick from here because all one can see is the trompe-l'oeil paintings of Sir James Thornhill. But we are standing on top of the inner dome, the light, again brick inner dome, which, as you can see, has an oculus in the center and allows us to look down into the space of the cathedral to see the Whispering Gallery and the floor of the cathedral below.
It took all of Wren's considerable talent to find an appropriate structure for the dome. He prepared endless preliminary designs and delayed making a decision until the last moment.
Well, here we are between the brick cone and the outer dome. We've seen the brick cone before. That's the thing that is carrying the great weight of the lantern above. But here you appreciate the lightness and elegance of this timber structure, which is the outer dome. As you can see, it's all built of wood. The dome is essentially wood covered by lead on the outside. And that's what you see from the famous silhouette of the Dome of St. Paul's. But it's not the real dome at all. It's all window dressing. So we've got three skins: the light outer dome, the brick cone that's doing the work, and the ceiling that you see from the inside. It allowed Wren to have this wonderful silhouette. It allowed him to have the ceiling level that he wanted on the interior, and it allowed him to provide the support. And so he was able to solve the problem of constructing a dome in a way that none of his predecessors had really been able to achieve.
Wren understood that his dome was a work of sculpture. There was no need for it to be load-bearing. Yet designing sculptural roofs continues to confound architects today. October 20th, 1973, the opening of the Opera House in Sydney, Australia. Her Majesty Queen Elizabeth II performed the ceremony. Yet behind the pomp and circumstance lay a still smoldering controversy, one filled with charges of egotism and incompetence and of political manipulation. The building's completion had been delayed 9 years. Its final cost was $130 million over its original $10 million estimate. In 1957, Jorn Utzon, a Danish architect, won the international design competition with a sketch of a soaring, sail-like structure. But there were problems from the start. For the first 3 years, Utzon decided to supervise the building not from Sydney, but from his home in Denmark, 15,000 miles distant. More serious was Utzon's insistence that the concrete roof shells be honestly self-supporting, even though their shapes were entirely inappropriate for the task. It took a decade to engineer the intricate pre-stressed concrete system that finally made construction possible. Under pressure to begin work on the project, the building's base was constructed before the design for the shells was completed. It had to be demolished and rebuilt. Amid further confusion, Utzon resigned or was fired. No one seemed quite sure.
A far simpler and certainly less costly structural system would have used steel frames to support the shells. But that was rejected by the designers because of their obsession with so-called honest structure. In a sense, they made the same mistake as the Renaissance builders because, like the domes, the importance of the shells lies in their appearance. They're primarily sculptural forms, and to insist that they be self-supporting is nonsense. But building sculptural roofs is only one of the problems that have exercised master builders over the ages. They ran into an entirely new set of problems when they started to build very tall buildings.
"800 years ago, as Europe emerged from the Dark Ages, an extraordinary burst of activity occurred. As trade grew and prosperity came, men built giant cathedrals, towering monuments to the glory of God. Gothic cathedrals were designed to portray the medieval relationship with God, to dwarf those who entered them, to inspire awe, and to remind man of his humble station. Cathedrals both created God's celestial temple on earth and reflected a newly emergent civic pride. In the 13th century, this cathedral at Amiens could hold the inhabitants of the entire city. And if the names of the men who built them are lost, their buildings remain, tribute enough. For the master builders, these cathedrals were often the work of a lifetime, but their splendor has never been surpassed. The real wonder of Gothic cathedrals lies not merely in their great height, but in the delicacy of their construction. They are built in a series of bays. On either side of the central nave, slender piers reach up to the vaulting and support most of the building's weight. On the exterior, the pier and flying buttresses resist the building's outward forces. The walls bear little of the load and can be opened up to admit light. With his collaborator, historian William Clark, and with the assistance of Bernard Foncarny, the Inspector General of French Historic Monuments, Robert Mark is investigating the intricate history of Gothic architecture. A full third higher than its predecessors, Notre Dame in Paris was designed to be the tallest Gothic building in history. Its vaults rise 108 feet above the floor. Higher still, the timbers of its immense attic bear witness to the complexity of the master builder's task.
I understand this is called the forest.
La forêt entière a été utilisée pour construire l'ensemble de cette charpente.
They must have used almost an entire forest to construct this. You could see the considerable numbers of timbers and the density with which they are in here.
This is mostly 13th century.
It's probably the original roof of the nave, the end of the 12th, early 13th century. And you can see lots of the original timbers. Look over there. You can see the original timbers.
Les bois, les clavettes de bois. Hein.
The weight of these long horizontals is carried by these hanging pendants to hold the whole thing up.
Vous voyez là, regardez.
The timbers were used in construction, and that's the reason they are built so heavily, in fact. But these were the main lifting devices in the construction of the building.
That's true. The roof went up before the vaults were put in place.
Cette charpente doit supporter le couvrement qui est en plomb et qui est très lourd.
That's true, and on the other side, of course, there's the very heavy lead. How much lead
210
is that?
tonnes.
That's right, more than 200 tons
Uniquement de plomb. Hein.
of lead alone were used in the construction of the roof.
The Notre Dame we see today is not the one its master masons built, or not quite. In the 13th century, soon after it was completed, rebuilding took place, and this elaborate system of buttressing was installed. But why were the changes needed? Because of its height, the cathedral had been a risky undertaking. Its designers may well have underestimated the engineering problems of the building. Mark's collaborator, William Clark, an expert on Notre Dame, set about reconstructing the original appearance of the cathedral. His task was complicated by additional rebuilding in the last century by Eugène Emmanuel Viollet-le-Duc.
In the 1840s, when Viollet-le-Duc took over as the architect of Notre Dame de Paris, the building was in a terribly dilapidated condition and probably in danger of literally collapsing. He worked on the building for more than 20 years, studying every part and every piece, and did extensive restorations that essentially preserved the building. On the interior, those restorations were very carefully documented, stage by stage, in his work journals. And we can see in a drawing like this exactly the evidence that he found. For example, when he analyzed the 13th century windows, he discovered the debris and fragments from the 12th century windows installed in the walls around, some under the roof, and was able on that basis to determine exactly the pattern of the original tracery, which you can see here, and the form and size of the original oculus openings, not to mention, of course, the size of the original 12th century window. Every course of stone is very carefully measured. The source of each is carefully recorded in the color chart here on the side of the drawing. This lengthy and very detailed study of the building led him, in some cases, to propose reconstructions for which the archaeological evidence got somewhat confused.
According to Viollet-le-Duc, The original buttressing system consisted of two upper flyers supported at their center by a pier buttress. One such set of buttresses does exist, but it is a 14th century addition added after the other huge flying buttresses were in place. For Clark, the key to the original configuration of the buttresses was contained in a drawing showing a curious embedded arch.
The thing he was most interested in was restoring the original 12th century roof line. That's recorded in the drawing, and that's what he put back with the 12th century windows. But for us, the most important thing is that arch embedded in the pier buttress. It's the only surviving evidence in the building that shows us that original form. All the rest disappeared when all the buttresses were rebuilt.
But Violet didn't realize that that curve represented the original flyers.
His drawing shows the arch, but he's only interested in the original roof line at that point. It took the rest of us to recognize that as the level of the first flying buttress, which was a much less complex system than exists now.
The arch reflects the shape of the original buttresses at Notre Dame. Then in the 13th century, a much more massive system was installed. There was good reason for these changes, as Mark's structural analysis revealed. Mark's technique is deceptively simple. First, a scale model of the cathedral's structure is cut from a sheet of epoxy plastic. Then it is loaded with weights to simulate the effects of wind or gravity and placed in an oven. When the model cools after heating, deformations caused by the loads are frozen in place and show up in polarized light.
This model represents the structure of the original nave of Notre Dame, Paris. And the model itself is scaled from the full-scale structure, and it's been loaded by a simulated wind load. The wind is coming from where I stand against the structure, and it represents pressures and suctions from a velocity of about 90 miles per hour at the roof level, which is probably the worst wind that the building has ever been subjected to. After the loading, we can take the model and place it in this instrument, which uses polarized light. It's called a polariscope. And by looking at the pattern that develops, we can find the way the forces are distributed throughout the actual structure. Where the force intensity is high, the patterns indicate lines very close together. Where the force intensity is low, as in this region of the pier, the lines are rather broad. The model also revealed regions of tension here at the end of the flying buttress and here at the end of the lower flying buttress. These are regions that we don't think the designer would have been very happy about, because in fact what happens there is that the stones are pulled apart, and the tension causes cracks in the mortar. And this would have to have been attended to, because water can get down into the cracks and cause the structure to destroy itself. So a great deal of care was probably required. Remember, these frames occur at many sections along the building, and that would have necessitated a great deal of care. And it's because of that problem, probably, that the structure of the nave was rebuilt early in the 13th century.
The master builders of Notre Dame had stumbled upon the greatest hazard for tall buildings. The wind's velocity increases with elevation. The pressure the wind exerts is proportional to the velocity squared. Pressures at the top of Notre Dame were much greater than anyone had foreseen. The builders here had pushed into unknown territory. They faced new challenges, made mistakes, and devised new solutions. Notre Dame established the fashion for flying buttresses. It was a fashion forged by necessity. As the Gothic style spread, cities competed to construct the grandest buildings. Here at Bourges, work began on a still taller cathedral even before Notre Dame had been rebuilt. The cathedral was to have an uninterrupted nave with vaults which soared 120 feet above its floor. The lesson of Notre Dame was not lost on this master builder as he set about his monumental task.
The problems at Paris caused a great change in the design at Bourges, which was then the tallest Gothic building. These elegant flying buttresses were not envisioned by the builder in the original design, but they were added as a result of the problems there. The builder at Bourges evidently learned from problems at Paris, and that represents a marvelous example of one Gothic builder learning from the experience at another building site.
Like Notre Dame, Bourges has two pairs of side aisles, although the inner pair are much taller. As news of the troubles at Notre Dame spread, a set of steeply sloped flying buttresses were added. Mark's experiments revealed that they may be the most effective of any in Gothic architecture.
There's not very much to see, in fact, in this model because the structure is so excellent. It's a very unusual structure from that period. The designer aimed his buttresses up at a very high angle, and the result is that everything is working extremely efficiently. When you view the pattern, what you see is some activity, but all of the activity that you see in this region, for example, is compression, and the stones are well able to take compression, so that's not very much of a problem. In the flying buttress region, where in the other buildings we always see a little bit of bending and tension, which causes some difficulty for the stones, in this case we see practically nothing.
The design of the buttressing here at Bourges was so successful that it uses 60% less stone than in the cathedral at Chartres, which was being built at the same time. But these buttresses were not widely imitated, even at Bourges itself, where the building's style changed after a pause in construction.
I'm standing at a point of transition. The eastern end of the building was built and completed by 1214, and then there was a hiatus for 20 years before the western end was begun. You can see that in the windows, in fact. The windows in the eastern end are smaller and round-headed, and there are much larger windows in the western end. There were other changes as well. The flying buttresses of the western end are much heavier than the original buttresses. Apparently, the later designer didn't trust the lightness of the original design. It's interesting that the original design wasn't used in any of the high Gothic cathedrals that followed Bourges. Apparently, they thought of it as a technical fix, which would be too inelegant for a monumental structure.
The French High Gothic reached a culmination in the Cathedral of Amiens. Its majestic vaults rise 138 feet above the nave. The clear-story windows flood the cathedral with light and produce a sense of space on a visionary scale. Amiens is the highest of any completed French cathedral, and building began in 1220, 25 years after Bourges. As its builders continued to refine the High Gothic style, they introduced more engineering innovations. The vaulting of the nave differs from the earliest cathedrals, for example, as Robert Mark explains.
One of the major changes in the High Gothic cathedral was the adoption of four-part vaulting. It was assumed that the vaulting was adopted in order to create a greater uniformity in the nave, and the vaulting was also assumed to be lighter than the earlier six-part vaulting. This was, it seemed appropriate for the lighter construction of the entire building. One can see the vaulting. The four-part vaulting is defined by the two cross ribs and the two diagonal ribs, then, which form the four parts of the vaulting.
When Mark studied the 4-part vaulting, he discovered that it was heavier than the 6-part vaulting used in earlier cathedrals like Bourges. There, a single pair of diagonals cross each pair of bays. So why had there been a change? The answer, it turned out, lay in the forces exerted by the weight of the vaults. They act in 3 separate directions: downward, outward, and most critically for the question of the vaulting, along the line of the cathedral walls. These forces push sideways against the neighboring bays, and it was here that the major differences between the 2 vaulting systems were revealed.
We were surprised to find that the thrust exerted down the bay is less than half as great in the 4-part system of Amiens than it is in the 6-part system at Bourges. The 6-part system there produced a force of 42,000 pounds. That's greater than a 20-ton truck. And all of this had to be supported during the construction. When the vaults are in place, the vaults lean against each other, so that force doesn't show up. But during construction, the end bay has to be supported, and you can see that it would be a great improvement and quite important to reduce that force in the construction of the much taller buildings.
Another of Mark's interests here centered on one of the characteristic features of the Gothic style: the pinnacles which decorate the tops of the buttress. As with the step rings of the Pantheon, he wondered whether they were purely decorative or if they played some structural role. Again, his model revealed what was happening.
The results of the model were rather surprising. We found the structure worked reasonably well. There's a bit of bending, as you can see in the flying buttresses, but not an overly great amount. But what surprised us particularly was the fact that here on the leeward side, we found some tension. The tension probably can be seen more clearly in the blue-black region when I rotate the analyzer, right up through this region. What's happening is that under the push of the wind, the building is bending into a kind of S-curve, and this upper portion of the S over here is in tension. The effect of dead weight, when added to the effect of the wind, reduces some of that tension, but a bit is still left, and it probably caused cracking in the stones, in the mortar between the stones, which was seen by the builders. The pinnacles, then, that sit right above that point on the outside of the buttresses, in fact, help to push the stones together.
The pinnacles are both striking visually and play an important technical role, a perfect blending of engineering and art, and a perfect example of the master builder's craft.
They were able to build these buildings because the designer and the builder were one, and the designer was intimately associated with the building. He was able to observe cracking, for example, and on the basis of that modify the design as necessary. That's not the way we build today. The designer works in the office, uses computer models and other data to assemble the plans that then go out into the field. For the Gothic builder, the building itself was his model, and he was able to modify the building on the basis of his observations of his great model.
With the advent of the Renaissance, Gothic architecture fell out of favor. It would take another 5 centuries for the true heir of the Gothic style to emerge. Skyscrapers are one of the greatest innovations in architecture in the last 100 years. Built around frameworks of steel, they are like Gothic cathedrals, tall and light, with a skeletal construction. For almost 70 years, their basic structure remained unchanged. But as buildings grew still taller and lighter, the cost of stiffening them against the effects of wind sharply increased. There was a simple solution to the problem, but it was long ignored. The Eiffel Tower, built in 1889. Almost 1,000 feet high and containing 10,000 tons of wrought iron. For 40 years, it was the tallest man-made structure in existence. Gustave Eiffel was an engineer by training, not an architect. In a series of bridges, he displayed a thorough grasp of the forces acting on large structures. When Eiffel began to build the tower, he designed it to act as a cantilever beam, anchored at one end, but free to sway at the other. Cross braces stiffen the tower's legs, so the whole structure acts like a rigid tube, evenly distributing the forces throughout. It took another 70 years for architects to adapt this design for their own buildings. The John Hancock Center in Chicago. This revolutionary building came from a collaboration between an architect and an engineer. Its most striking feature is that its supporting structure is on the exterior. Like the Eiffel Tower, a giant network of vertical and diagonal elements support its weight and resist the effects of wind. And like a Gothic cathedral, it permits lightweight construction.
The distribution of loads in this building is not so dissimilar to that in a Gothic building. In fact, the major forces supporting the building are along the exterior, very much as we saw along the exterior of a Gothic cathedral.
Stan Carista is an engineer and a senior partner at Skidmore, Owings & Merrill.
One of the interesting factors, if we look at this three-dimensionally, is that the actual diagonalization system has taken a solid box, allowed it to be opened up, but structurally really achieving a three-dimensional box in which each of the four faces of the buildings actively participates. So as the wind pushes on one side of the building, it's not only resisted by structural elements along the parallel face, more importantly, it's resisted by elements along the perpendicular faces of the building. The corner columns do have the maximum loads because in any of the structures of this type, there's a certain amount of what is known as shear lag effect as we go around the corner, which doesn't provide for the full and complete distribution of windward or leeward face forces.
We're simulating the effect of the wind, and the building is deforming and recovering essentially and deforming again, and you can actually see the deformation of the various members.
And the diagonal members also are lengthening and shortening as we look at it. It's to an exaggerated scale. Now, the other interesting factor is that...
Excuse me, the time is exaggerated also.
Time is exaggerated, certainly. The actual period of the building as it sways from one side to the other is in the order of magnitude of approximately 7 seconds. So that's a very slow motion, maybe 30 inches of maximum movement to one direction. So back and forth that amount, it's taking a full 7 seconds to go back and forth.
The John Hancock Building in Chicago, with its distinctive cross-bracing, cleverly combines architectural and structural considerations. In Boston, the John Hancock Building has a very different tale to tell. Designed by I.M. Pei and Partners, the building won critical acclaim in architectural quarters, yet raised a storm of angry debate. From the beginning, the idea of erecting a large skyscraper in Copley Plaza was controversial. Its presence might well disrupt the square with its collection of historic buildings, Trinity Church and the Copley Plaza Hotel.
As you can see, the design is settled on an extremely slender, tall building clad in mirrored glass. The tower was supposed to fade into the background, reflecting images of the surrounding buildings. But technical considerations seem to have been placed on a back burner. How successful the architect's solution is, you can judge for yourself. Aesthetic judgments are a matter of taste, but technological evaluations are not.
The Hancock's troubles began during initial excavations when the surrounding land subsided. Cracks appeared in the facade of Trinity Church. The church sued and received $11 million in compensation. Then the windows fell out. It started as a trickle in 1971 and grew to a deluge by December 1972. During a single windy night, 43 windows were cracked, some by the wind, others by falling glass. By the following July, almost 2,400 of the tower's more than 10,000 panes had been replaced. So many windows had been patched with plywood that Boston's fire chief declared they constituted a fire hazard. Extensive modifications were carried out, and occupancy of the building was delayed 3.5 years. A complicated legal battle ended with a secret out-of-court settlement, and exactly what went wrong has never been revealed. It is possible to make intelligent guesses, however.
Clearly, there were many problems with the building, but the greatest problem seems to have been one of stiffness. The building is rather narrow, and it probably twisted in the wind, which made me wonder whether the workers constructing the building observed that motion, even before the windows were fitted. Afterwards, they installed mass dampers, huge moving weights near the top of the building, and additional longitudinal members designed to reduce the motion of the building. In 1977, the American Institute of Architects awarded the design award to the architecture firm for the design of the building. And they cited in the award the fact that it beautifully reflected downtown Boston, but they said nothing at all about the major technical flaws, including the expensive problems with the windows. For an influential portion of the profession, obviously, appearance was all.
The analysis of ancient buildings is proving more fertile than anyone could have expected. New architectural styles, such as Gothic cathedrals, emerged not suddenly, but from their builders' past experience. As these monumental structures grew larger and taller, the master builders learned from their predecessors' mistakes. They took note of their solutions and modified their own designs accordingly. Perhaps that is why they so often successfully integrated engineering into their architecture. For Robert Mark, architects today have lost touch with the lessons the old buildings teach. The master builders did not simply design, they also built. It is that tie to the bricks and stone that, according to Mark, the modern architect has broken.
This powerful design technique is all but lost to the profession today. Perhaps many of the technological fiascos of the type that we've seen could be avoided by more feedback from the building site into the design office. Architects tend to work far removed from the site, and effectively, they've lost touch with the principles of the ancient master builders. As the philosopher George Santayana observed, those who fail to remember the past are condemned to repeat it.
Les anges dans nos campagnes ont entonné l'hymne des cieux, et l'écho de nos montagnes redit ce chant mélodieux. Gloria
For a transcript of this program, send $4 to Nova, Box 322, Boston, Massachusetts 02134. Please be sure to include the show title. Major funding for Nova is provided by this station and other public television stations nationwide. Additional funding was provided by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And by the Johnson & Johnson family of companies, supplying healthcare products worldwide.